Today's warm-up, both of these questions are things that you should be able to answer after having done the RA and the FET last week. By the way, if you didn't turn in the FET last week from Friday, then please make sure you get that turned in. I did put those grades in this morning, so you can check and see if you have a 0, then you'll know that you're missing it, because I had 2 people in here that did not turn that in yet. Okay, but as I said, we're going to go over the warm-up first, and then we are going to be taking quite a bit of notes today, and then you do have a homework assignment, which probably will end up being homework, unless we can get through these a little bit quicker. So if you've got side conversations, let's bring those down to a close so that we can get to it. The warm-up question says, where do the charges come from when you turn on a light? So think back to your RA last week. When you turned the light on, when you connected all those wires, where did the charges come from? Or if I flip the light switch in this room, where do the charges come from? Sorry? I don't know. All right, anybody have a guess? Okay, so here's the deal. I heard the guess I expected to hear, and that is a battery. Okay, they are already present in the wires. Okay, but it is, listen up, it is a very common misconception that they come from the battery. They don't. Okay, remember the charges moving through the wires are actually electrons. I know we talk about conventional current, we assume they're positive charges moving, but in reality they're electrons. Electrons are found in atoms. Atoms make up everything, including the wires, including the battery, including the switch, okay, including the light bulb. Okay, and so those atoms are already there, and thus the charges are already there. They're already in the wires, they're already in the light bulb, they're already in the switch, they're already in the battery, they're everywhere. The battery provides the push to move them. It provides the energy source to move them through, but it doesn't make them. Okay, so that is a common misconception. You might want to make a note on your paper about it. I think it was mentioned in the FET, but if you didn't write it down there, or if you didn't remember, you might want to write it down again. All right, the second question in the warm-up says, will either bulb pictured light up? If so, which, and why or why not? So let's start here. Will either of these light bulbs light up? Yes. Will both of them or just one? Just one. Okay, which one lights up? Okay, so again, I know Tier knows. I don't know if anybody else knows right now, but the one on the right. Okay, so listen up. In order for the light bulb to light up, the bulb has to be part of your complete closed loop, meaning that the charges have to be able to flow from the battery, through the wires, through the light bulb's filament, and then back to the battery again. The only bulb that does that in this picture is this one here on the right-hand side because of the way that the wiring is in the light bulb. And we talked about this last week as well. But the bulb has to be contacted on both the bottom and the side because of the wiring, so that the charges can go in this case, through the bottom. If we're talking about conventional current, they'll flow in through the bottom, through this filament, and then back out through the side. Okay, and so it's part of that loop that the charges are going to move through. So only the one on the right. The one on the left will not light up because there is nothing contacting the side of this bulb, meaning that those charges don't have a pathway out and back to the battery again. Okay, so they're not going to be flowing through it without a pathway. So again, only the bulb on the right. You need to make sure that you answer both of these questions in My Open Math for your warm-up, and then make sure that you submit it. Okay, so today we're going to take a lot of notes on kind of the basics that help to explain the different types of circuits that you've built in the RA and that you're going to see throughout this unit. And then you do have an assignment, 1104.1 Circuit Basics Problem Set. Sorry, I'm going backwards on accident. What is going on? Okay, so let's go ahead and come back to Ohm's Law. Okay, Ohm's Law was in the FET, so you should already have it in your notes, but it was not a whole lot of information. So again, if you didn't copy it down, or if you did, you might want to add to it. But Ohm's law explains the relationship between the electric potential difference or voltage in a circuit, the current flowing through that circuit, and the resistance of the resistors along that pathway, okay, on the wire. So the resistors could be like an actual resistor like we used in the RA, or it could be a light bulb. A light bulb is a special type of resistor. Okay, but the equation for Ohm's law that states this relationship is voltage equals current times resistance. The variables that we use, voltage is delta V. Voltage, by the way, is also called electric potential difference. And that's where the delta is coming from. It's talking about the change in the electric potential energy per charge. Okay, so this has to do with how much energy the charges have. Current is represented by the letter I, and then resistance is R. Now when you read a problem, or maybe you're not even reading a word problem, you're just looking at a diagram with some labels on it, you need to be able to identify which of these is your voltage, which is your current, and which is your resistance. In order to do that, it would help you if you knew what the variables were, the units were for each of those variables. And so that's what this is right here. Voltage, or electric potential difference, is measured in volts. That's the easy one because it's obvious that that goes together. Current, which is represented by the I in my equation, is measured in amps or amperes. Now we shorten that to amps, and we can shorten it further by just labeling it as a capital A. And then resistance is measured in ohms. Now ohms is represented by a Greek letter. It's a capital omega. But this is the unit that you will see next to a value for a resistance will be ohms, and you'll see this omega symbol, or you might see the word ohms written out. Okay, but you need to be able to identify which one's which so that you can appropriately place them into that equation. So I would, if I were you, write down what these units are as well. Okay, volts, amps, ohms. By the way, guys, if you want to open up these slides on your own screen, I may go faster than you're writing, and so if you want to have them opened, I'm currently on slide 12. We're going to do a practice problem for Ohm's law. It says, what current flows through a hairdryer plugged into a 120 volt circuit if it has a resistance of 25 ohms? Again, I can tell by looking at this, I see current, I see a voltage because I see 120 volts, and I see resistance. So this is obviously an Ohm's law problem. Voltage equals current times resistance. I know that this is my voltage, 120 volts, so I'm going to plug that in here. I know this is my resistance because it says resistance of. If it hadn't said that, I would still know it was resistance because of the unit. Okay, but I have that plugged in for R, and I'm going to solve for I. In order for me to solve for current, I need to isolate that variable, which means I need to divide both sides by 25. And so 120 divided by 25 gives me a current of 4.8. Guys, what is my unit for current? What did we just say? Amps. Okay, so we also have to make sure that we label the right unit. Okay, but 4.8 amps. You can label it with just a capital A, or you can write out the word amps if you prefer. Okay, so pretty basic 3-variable equation. Of course, we know our math is going to get trickier than this, but the Ohm's law itself is not a very difficult equation. Now, we can apply it to more complicated scenarios than this, okay? And we'll do that later on in the period. This equation for power is one that was not in your FET, and therefore you have not yet seen it, so you do need to copy this one down in your notes. If you had already copied the other one, you didn't have anything to write. Power, electrical power, is the rate at which electrical energy is supplied to a circuit or consumed by a load. Power is equal to voltage, or electric potential difference, times current. So P equals delta V times I. That's the equation you are going to get on the board or on your formula chart, just the first one. However, you can derive 2 other equations by substituting Ohm's law into this equation. We just learned that Ohm's law states that voltage equals current times resistance. So by substitution, I could say current times resistance times current. I times R times I, which would give me this equation, P equals I squared times R. Okay, so I can get that by substituting one equation into the other. Or if I rearrange Ohm's law, and that's the way it was in the PhET, was I equals delta V over R. Okay, I could substitute that in right here for I. Delta V over R times delta V is delta V squared over R. Now, you don't have to memorize these equations. You don't even have to necessarily use them. If you can't remember those or derive them on your own, you can simply solve some of these problems in 2 steps. You could use Ohm's law first and then the power equation, or the power equation first and then Ohm's law, depending on what you're trying to solve for. But if you memorize these equations, or if you can derive them on your own, it is shorter. Okay, it is a little bit of a shortcut if you can do it in a single step instead. Okay, but you will only be given the first equation, not the 2 in the box. You can get those on your own if you need to. Power, by the way, we've seen power before when we did mechanical power, and it's still the same unit. It is still watts. So it's a capital W as the unit for power. So let's look at an example problem. It says, calculate the resistance of a toaster oven if its power is 800 watts when connected to a 110 volt outlet. Okay, so looking at this question, I know that I have power and voltage, and I can use power and voltage to find current. However, the question's not asking me for current. So I can do this in 2 steps, or you could use one of those little shortcut equations we just saw if you can memorize them. Because like I said, you're not going to get those. So I'm going to do this in 2 steps, because you could always do this with the information that you have. We're going to solve for the current first, and then we're going to find resistance afterward using Ohm's law. So we're going to use the power equation, and we're going to plug in my power is 800, my voltage is 110. So we're going to solve for current. 800 equals 110 times I. To get I by itself, we're going to divide both sides by 110. 800 divided by 110 is 7.27 amps. Okay, that's not my answer because the question doesn't ask for that. The question asks for resistance, but that is the first step to finding my answer, because now I can use Ohm's law. Ohm's law states that voltage equals current times resistance. I just found the current, and the voltage is in the question. So I can now solve for resistance. If I plug in, here's my voltage, 110 equals my current, 7.27 times R. Divide both sides by 7.27 to isolate my variable, and 110 divided by 7.27 gives me a resistance of 15.1 ohms. Okay, so 2 steps to solve this one, or again, you can use one of those equations if you can derive them or memorize them. Questions about this problem? No? All right, so again, as I said, these will get trickier because we are going to be applying both Ohm's law and our power equation to specific circuits that have more than one resistor. So it's going to be a little trickier than this, but we're going to talk about how to do that as we get toward the end of the period today. Okay, so whenever we look at circuits, I told you that sometimes instead of a word problem, you're going to just have a diagram. Those diagrams are called schematics. We can represent a circuit with this type of diagram where we use different symbols to represent the different components of the circuit, and it's a lot easier to look at or read than looking at an actual picture of a circuit that might look something like this. Okay, so these are the most common symbols, or at least the ones you need to know for this class. So if you're looking at a schematic and you see these symbols, you need to know what they mean. So if I were you, I would copy them down. Battery is going to be represented by alternating long and short lines that are placed perpendicular to the wires of your circuit. That looks something like that. Depending on how many cells your battery, how many batteries you're using, you'll have varying numbers of those lines. It could just be one long line, one short line if you only have one battery. Okay, but if you have more than one of them placed together, you'll see it represented like this. The long line is the positive terminal. The shorter line is the negative terminal. A resistor is going to be represented by a zigzag line, like this one. A light bulb by a circle with a little loop inside. It kind of looks like a bulb with a filament in it. Wires are just going to be straight lines. A switch, if you have a way of turning your circuit on and off, the switch kind of looks like a doorway that can be opened or closed. And then these two are the tools that you saw in the FET, an ammeter and a voltmeter. They're going to be represented by a circle containing an A for ammeter or a circle containing a V for voltmeter. So again, these are the most common symbols that you'll see. There are lots of other symbols, and if you start looking at pictures of circuit schematics online, you're going to see some symbols that you may not even recognize, and that's okay, because we're only really focused on these in here. But there are definitely a lot more things you can add into your circuits than just this, but we're not doing that. All right, so if you were to see a circuit like this, if you built something where you had a battery connected to a light bulb with a switch, you could draw a schematic of it by just pulling the symbols in. So my battery symbol, my light bulb symbol, my switch symbol, and then connect them with lines, and you get something like this. Okay, where I have my battery connected to these wires that contain my light bulb and my switch. So again, you're not going to draw them as often as you are going to have to interpret them, but you still should know kind of the general rules for both, and you do need to know what those symbols are. All right, so here are two different circuit schematics for a series circuit and a parallel circuit, and these are two circuits that you guys built in your RA last week. Okay, so the one up here on top, these bulbs are connected in series. The one down here on the bottom, these bulbs are connected in parallel. And again, you built both of these in the RA with those actual physical materials. And so we're going to talk now about the difference between our series and our parallel circuits and explain some of the things that you saw in the RA. But we're going to start with a definition. A series circuit is a circuit in which the current has only one pathway to follow. There is only one loop. So the charges in this circuit will leave the battery, move through the wires, move through both of these light bulbs, and make their way back to the battery again, where they'll increase in energy and repeat that whole process. And you have this constant movement of all these different charges through those wires. Okay, but they all have to take the same pathway. This is kind of what you would expect to see in a circuit with two resistors or two light bulbs. The battery increases the energy of those charges. You'll notice these charges that are moving in this circuit are represented as positive charges. That's because this is representing conventional current. We know it's actually electrons moving, but our model is this one. Okay, and so I have these charges. They enter the battery with minimum electric potential energy. So they're depleted of energy. The battery does work on those charges, increasing their electric potential energy, and they leave the battery red at maximum energy. And then as they flow through the circuit, you have energy dissipated at your resistors. So it loses about half of its energy at R1, and it loses the other half over here at R2. If R1 and R2 are identical, that's exactly what would happen. You'd have half of your energy dissipated at R1 and half at R2. And that could be dissipated as light, if these are light bulbs, or heat. I don't know if you guys touched that resistor. It did get warm. But you're going to have energy changes here. They're specifically losing energy from the circuit at each of these points. And then they flow back into the battery, and the whole process is repeated, of course, until your battery's dead. All right, so follow-up question here. What changes can increase the resistance in this circuit? In the FET and in the RA, there was a discussion of different things that affected resistance. You guys remember what those things were? There was like a diagram in the FET. What do y'all think? Anybody remember one of them? The material the wires are made out of. That was one. Okay, what else? The thickness of the wire. So if I wanted to increase the resistance, let's start with the thickness. If I wanted to increase the resistance, I would need thinner wires. Okay, that's why that light bulb filament had more resistance, because the filament wire was really tiny. Okay, I could also use longer wires. I don't know how closely you looked at the filament in the bulb because it was so small, but that filament wasn't just a small skinny wire, it was a small skinny coil of wire. So they increased the length of it by making it into a spiral. Okay, and so longer wires also increase your resistance. Using a less conductive material, that's the one that Tiara mentioned, so a less conductive material would increase your resistance. There was even a table that listed some different conductivities, but specifically you need to know that your most conductive materials are silver, copper, gold, and aluminum, in that order. Okay, you don't necessarily have to know that order, but those are your most conductive materials. That's why when we put the resistor in the circuit, we increased resistance, because that resistor was made out of carbon. That's what was inside of that thing. Okay, and it does not flow very well through carbon by comparison to the copper wires that were surrounding it. Okay, and so that increases resistance. Higher temperatures would increase resistance. And it told you in those notes that you're going to have more resistance anytime you have more collisions. So if you think of these wires like a roadway or like a hallway, the thinner they are, the more likely you are to collide with stuff. Okay, the longer they are, the longer you have to go, the more likely you are to collide with stuff, because obviously electrons aren't exactly steering their way through there. They're just kind of pinballing their way through there and colliding with stuff along the way. Okay, but higher temperatures does that too, because when you increase temperatures, those particles all move faster, and so you're going to have more collisions. Okay, and so this would also increase your resistance. And then the last one would be if you were to add another resistor like right here in series, that would also increase the resistance of this circuit. Okay, so that's our series circuit. One single pathway, our charges have to flow through all the resistors on that loop. A parallel circuit, on the other hand, is a circuit in which the current has multiple options or pathways that it can follow. There is more than one loop. And so if you look at the schematic right here, those same charges that leave the battery, when they get to this point right here, this junction, some of those charges are going to turn and go through this light bulb. Some of those charges are going to go straight and go through this light bulb, and then they'll rejoin each other here as they go back to the battery again, like this. Okay, and so here it looks kind of similar. My charges enter the battery having minimum electric potential energy. The battery does work to increase their electric potential energy, and so they leave and they're red. And then at this junction, some of them turn and go down, some of them continue forward. And so some of them go through R1 and some of them go through R2, but they're not going through both because they're on two separate loops. They rejoin each other here, they make their way back to the battery. This is what it means to have two resistors in parallel. Okay, so these are, the charges only go through one or the other. So again, just kind of reviewing, what changes can increase current in this circuit? Guys, Ohm's law shows you that current and resistance are inversely proportional. So if you have more resistance, you have less current. If you have less resistance, you have more current. So I'm effectively asking you the exact opposite question, because in the previous one, I asked for increasing resistance. Well, increasing current means decreasing resistance. So we can answer this question in pretty much an opposite way. So instead of thinner wires, I want thicker wires. That's going to increase my current, decrease my resistance. Instead of longer wires, I want shorter wires. Instead of a less conductive material, I want a more conductive material. So instead of aluminum, I'm going to use silver or copper. Okay. Cooler temperatures, again, things that are going to have fewer collisions. Okay, it means that my current's going to be greater. But this last one's a little different because my last circuit was a series circuit. This one's parallel. In my series circuit, when I added more resistors, I increased my resistance. That's not true for a parallel circuit. If I were to add another resistor in parallel, I would actually decrease my resistance and I would increase my current. And we're going to talk about why that is in a minute. I can kind of quickly mention it right now, but if I were to add another one out here, for example, these charges right now have two different pathways to go on. If I added a third, they'd now have three pathways to go on. Think of it like traffic on a road. If there's only one road in and one road out, like in a series circuit, there's a lot of traffic. Okay? If there, on the other hand, are three different roads to get there, there's a lot less traffic. traffic, there's less resistance, okay, and therefore the flow of rate of cars, which would be analogous to current, the flow of the rate of charge, okay, the rate of charge flow would increase. You'd have a greater current, a greater flow of the cars if you have more pathways. It's the same idea. So adding another resistor in parallel will actually increase your current, not decrease it. It is the exact opposite of a series circuit. We're going to talk more about that though. All right, so let's come back to these. When you built these circuits in your RA, you used the same batteries, you used the same light bulbs, and yet the bulbs were not equally bright. Okay, because when you built it, the brighter bulbs were in that parallel circuit, or at least they should have been. Okay, your parallel circuit had brighter bulbs. And again, it all comes back to resistance. We don't look at them the same way. When we add more resistors in parallel, it does something different than when we add them in series. And so we need to talk about the equivalent resistance of the circuits. Okay, if you want to write down a definition, you can. Equivalent resistance indicates the total resistance of the circuit. We calculate it differently for our series and parallel circuits. So let's take a look at the schematics instead of the diagrams from the FET. And let's say that we have 3 ohm light bulbs. They're all the same. The same light bulbs, all of them are 3 ohms. Okay, and we could figure out what our total resistance is, but I'm going to tell you right now it's not the same for these 2 circuits. Okay, because if I want to figure out my equivalent resistance for my series circuit, my equation is really simple. My total resistance would equal R1 plus R2 plus however many resistors I have. So in this case, that's 3 plus 3, which means my total or equivalent resistance is 6 ohms. So this circuit that contains 2 3-ohm light bulbs would be the same as a circuit that contained 1 6-ohm light bulbs. They're equivalent to each other. That's what it means by equivalent resistance. It's equivalent to a single 6-ohm resistor. Okay, so that's a series circuit. That's easy. Add them up. That is not how you calculate it in parallel. In parallel, this is my equation. And guys, I would strongly encourage you to copy this down. Okay? Because if I want to calculate the equivalent resistance in parallel, when I add another resistor, I'm adding another pathway. It's actually going to decrease the total resistance of my circuit. And here's the mathematical equation for that. 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over however many resistors we have. So in this particular problem, it looks like this. 1 over my equivalent resistance equals 1 over 3 plus 1 over 3. Guys, what's 1/3 plus 1/3?
2/3.
Good. 2/3. I know that y'all aren't necessarily fresh with adding fractions, but just as a quick reminder, when you add fractions, you have to have a common denominator, which I do. They're both 3's. Okay, but when I add them, I'm only adding the numerator, so please don't tell me it's 2/6 or anything like that. Okay, it's not. Okay, it is 2/3. So you only add the numerators. Now, that's not the answer, because that's not equal to RT. That's equal to 1 over RT. So you're going to add your fractions, and then you have to flip it. Get the reciprocal, inverse, whatever term you want to use. That becomes 3 over 2. 3 over 2 is 1.5. Okay, and so the total resistance of this circuit is 1.5 ohms. So the first one was 6. This one's 1.5. Sorry, I thought I had them both on the same screen. Okay. So when I added a resistor, I actually have half the total resistance that I had before. So adding them decreases my resistance. Because they're both 3, and I have 2 of them, I can just divide. 3 divided by 2. If I added a third one, 3 divided by 3. Okay, but if they were different resistances, you would have to calculate it with that equation. All right. So this kind of summarizes what we just talked about, but adding resistors in series increases total resistance because all of those charges now have to go through another resistor. So if I added another 3 ohm light bulb on my series circuit, now it's 3 plus 3 plus 3 because they all have to go through all of them. However, if I add another resistor in parallel, I'm not just adding another bulb, I'm adding another path back to the battery. And it decreases the equivalent resistance because it means that I have more pathways. Each additional resistor in parallel adds another loop. And so it actually decreases the total resistance of the circuit. This is where students make mistakes because you now have two different sets of rules depending upon what type of circuit you're looking at. Okay, and so you have to make sure to identify which one you have first. Or if you understand the basic rules governing the circuits in the first place, you can apply them to any circuit you're looking at. And this is that first rule, okay, that governs all of our circuits. So this is called Kirchhoff's first law. It is also known as the junction rule, okay, or the current rule. And it states that the sum of all currents flowing into a node or junction equals the sum of the currents flowing out of the node or junction. It means that the current flow out of a battery equals the current flow back to the battery. And it's also known as conservation of charge. Effectively, if we have charges moving through the wires, there's always the same number of them. So if I have a certain number of charges that flow into a light bulb, I have the same number that flow out of the light bulb. It's basically conservation of mass, or conservation of matter. Okay, and so this is known as, again, Kirchhoff's current rule. So let's look at an example, or junction rule, it's the same thing. So current flow out of the battery equals current flow back to the battery, or into a node equals out of a node. So here, my charges are going to flow through this circuit. Here's the pathway. They have to go through the 4 ohm resistor, they have to go through the 2 ohm resistor, they have to go through the 12 ohm resistor, and then they make their way back to the battery again. Okay, and so if I were to measure my current at different points, the amount of current flowing in through A1 would equal A2, it would equal A3, because they're all on the same loop. So the amount of current that flows into my 4 ohm resistor, which would be what's here at A1, equals A2. And the amount of current flowing into the 2 ohm resistor from A2 would equal what comes out over here. And same thing here, what goes in here equals what comes out. And so all of these have equal currents because they're all on the same loop. So we can take Kirchhoff's current rule or junction rule and we can say that in a series circuit, the current's the same at all points. A1 equals A2 equals A3. Okay, we can also apply this same law to a parallel circuit. Okay, but in a parallel circuit, when my charges leave my battery, some of those charges follow this red loop, some of those charges follow this blue loop, and some of those charges follow this green loop because there are 3 loops here, not just one. Okay, and so it's the same rule though. The current flow into a junction equals the current flow out of a junction. So going into this 4 ohm resistor, the current here would equal the current coming back out the other side. Okay, or just looking at the red part here, this equals this, or the blue part, this equals this. And so I could rank some of these. Here are a bunch of different ammeters measuring current, A1 through 5. Okay, and I know that the total current here at A1 would be equal to the total current over here. I just don't have an ammeter here. Okay, and I know that because they're all equal, when these things split, they come back together. It's the same amount of current that I had when I went into that node or junction. Okay, and so if we were to rank them in a parallel circuit, again, your current splits at the junction. This circuit has 3 loops. You might want to write this phrase down. The charges prefer the path of least resistance. You guys have probably heard the phrase path of least resistance before. Okay, it comes from circuits. Okay, well, in terms of the science part. I'm sure people have used it in other ways as well. I know that they do. But you can apply that phrase here. Okay, so the charges prefer the path of least resistance. Okay, and so if you look at these and were to rank them, now obviously you have the most current through A1 because all the charges have to go through it. Okay, all of them. So A1 has the most. A3 would be the next most because it's both of these together, the blue and the green. By the way, I would strongly encourage you to color code your loops like I just did because it's really easy to tell that this one's got 3 different sets of charges going through it, this one's got 2 different sets, and the rest of them only have 1. If you color code it, you can see it really quickly. Okay, so I would strongly encourage you to get some highlighters or different colored pens or something. All right, so if I were to rank them A1 and then A3, and then after that, now is where I go back to this, path of least resistance. So A2, A4, and A5 each only have 1 set of charges, but they're on 3 different paths. So which one has least resistance? Okay, well, that's going to be the 2 ohm resistor next. That's the smallest resistance. So A4 is next, and then A2, and then A5. And so that's where that ranking comes from. And again, this will be easier once you've practiced it some more, and we'll show you how to do the math too to actually prove this and actually calculate those currents. But you should be able to get an idea of how to rank them without any math. All right, using Kirchhoff's first law. By the way, A3 equals A4 plus A5. So this one equals whatever is here plus whatever is here. Again, that's what the junction rule states, that those currents into equal out of the node. All right, loop rule. So this is Kirchhoff's second law. Okay, so we had our junction rule, now we have our loop rule. The loop rule states that the voltage drops at the resistors or bulbs along a loop must add up to equal the total voltage of the battery. Okay, this also means that the sum of all the voltages around a loop is equal to 0. And that's because the battery adds energy in, and then you lose that energy at the different light bulbs. And so if you were to add up all of those, you'd have like, negative 12. Positive 12 at the battery, and then you'd have -6 and -6, or whatever. Okay, and so your sum equals 0. And this is based on conservation of energy. So we just looked at basically conservation of matter as it applies to circuits, and now we're looking at conservation of energy as it applies to circuits. It's also known, by the way, as Kirchhoff's voltage rule. Okay, but again, the voltage drops, that's going to be your change in electric potential. Okay, so the electric potential energy per charge change at the battery has to equal the amount lost at the resistors on each loop. So, again, let's apply it to a circuit. So here's my same series circuit. The voltage drops at each of these resistors, I have 3, 4 ohms, 2 ohms, and 12 ohms. These voltage drops have to add up to 24 volts. That's what Kirchhoff's second law says. Okay, is that they have to add up to the voltage of the battery. Okay, there are multiple resistors on the same loop in a series circuit. The total voltage drop for each will add up to the battery's voltage. And again, I'm going to show you how to calculate these later on, but right now we're just talking about it conceptually. Okay, so in a series circuit, you're going to have voltage drops here, here, and here. Now, I will say this, these are not going to be the same voltage drop because the resistors aren't the same resistance. You're going to have a bigger voltage drop at this 12 ohm resistor than you have at the 4 or the 2, and then the 2 will be the smallest voltage drop. Okay, so higher resistances result in larger voltage drops on this single loop. This, by the way, if these were light bulbs, they would all be different brightnesses. Okay, you saw that in your circuit as well when you had a higher resistance bulb hooked up with a lower resistance bulb. This one was brighter because you had a higher voltage drop, a bigger change in energy. More energy was dissipated in the form of light. All right, let's apply it now to parallel. Same rule, but now at a parallel circuit. The voltage drops at the resistors along a loop must add up to a battery. Well, guess what? These have only one resistor on each loop because they have 3 different loops. So the red loop has one resistor, so guess what? The voltage drop is 24 volts. The blue loop has only one resistor, so guess what? Its voltage drop is 24 volts because that's the battery's voltage. There's nothing to add to it. Same thing with the green one. The green only has one resistor, so the voltage drop here is also 24 volts. In a parallel circuit, your voltage drops are all equal to each other, and they're all equal to the battery because each of them is on their own loop. Okay, and that's what this says over here. This circuit has 3 loops. Each of these loops has only one resistor, thus the voltage drop at the resistor on each loop equals the battery's voltage. So each of these would have a voltage drop of 24 volts. You can see the voltage drop here. It's the color change. Okay, again, voltage drop represents your electric potential difference. So it's the change in the electric potential energy per charge. So here you have half of its energy being lost. Here's the other half in series because they have to add up to the battery. The battery changes them from blue to red. The resistors make them go from red back to blue. On the parallel circuit, though, the charges going into like R1 start out red and they leave blue. All of the energy is lost here. Same thing here. The charges going into R2 start out red, they leave blue. All of the energy is lost here. So the voltage drops at those resistors are equal to the battery voltage. I know the animation's not super nice and clean on the Promethean. It looks much better on my slides. But you can also see a difference in how fast they're flowing. Again, when we added these second pathway, the second resistor in parallel, we increased the current. You can see that. This is moving slower on the left. These are moving faster on the right. So you can also see that in the animation. So here's a summary of Kirchhoff's laws. The first rule stated that current leaving the battery must equal current returning to the battery. Charge is conserved. We have the same number of electrons the whole time. Okay, in a series circuit, that means that your current's the same everywhere because there's only one loop. In a parallel circuit, it means that each of your loops have to add up to the total because the amount going into that junction has to equal the amount coming back out. The second rule states that the voltage drops at the resistors or bulbs along a loop must add up to a battery's voltage. So in series, they just add up to the battery because they're on the same loop. So if they're all the same resistance, and let's say you have a 12-volt battery and 3 resistors, then it'd be 4, 4, 4. Okay, they would add up to 12. Okay, but on parallel, all of them are on separate loops. And so all of them are equal to the battery's voltage, and they're all also equal to each other. So again, if you can remember these rules, you can apply them to any type of circuit you see, and you don't necessarily have to memorize this is series, this is parallel, if you remember Kirchhoff's laws. So let's see if we can apply some of this stuff to our circuits. These are the same ones we were just looking at. Both of them have a 24-volt battery. Both of them have 3 resistors, 4 ohms, 2 ohms, and 12 ohms. And this first question says, which has a greater equivalent resistance? And again, I could answer this without doing any math because I already know. Okay, and hopefully you do too, but let's go ahead and do it with the math. Okay, let's find the equivalent resistance of this series circuit first. That one's really easy. I just add them together. And guys, this will be a good example for you to copy down. 4 plus 2 plus 12 is 18 ohms. Okay, so the first one has 18 ohms of resistance, but let's do the parallel one. This is the one I would encourage you to write down because I know y'all can add 4, 2, and 12, but this one, 1 over RT equals 1 over 4 plus 1 over 2 plus 1 over 12. Again, just a quick reminder. You cannot add fractions unless you have a common denominator, unless you're making the calculator do it. We're going to do this by hand. Okay, because honestly, I think it's faster than typing fractions in the calculator if you have easy enough numbers. And these are easy because I can find a common denominator for 4, 2, and 12. That common denominator is 12. So 1/4 is 3/12. 1/2 is 6/12, and then I have 1/12. I can add those together. 3/12 plus 6/12 plus 1/12 is 10/12. Okay, and again, that's not my answer. I need the reciprocal. Okay, that is 1 over RT. Now we flip it. 12 over 10 is 1.2. That's why I said it's faster to do it this way. Okay, but I'll show you how to do it in the calculator later on. So those are my resistances, guys. 18 ohms versus 1.2. I told you adding more resistors in parallel reduces your equivalent resistance. Look at that. Okay, 1.2 ohms, much smaller. Greater equivalent resistance in series, greater current will be where you have less resistance. That's going to be your parallel circuit. Okay, so it's kind of a little quick recap of some of the stuff we talked about. All right, back to Ohm's law. Now we're going to apply Ohm's law to a circuit. Instead of just a single word problem with one number for resistance, now we've got 3 resistors. We're going to use a table to help us organize it. And I would encourage you to draw this table on your paper because it is a helpful way, especially when you're first getting started. It's a really helpful way to organize it. But honestly, I use these the whole time, not just on the first day. So we're going to label our resistors. I have 3 of them. My first one's 4 ohms. My second one's 10 ohms. My third one is 2 ohms. And my total resistance is easy enough. It's a series circuit. I don't have to mess with fractions. I just get to add them up. 4 plus 10 plus 2 is 16 ohms. Okay, so we're going to add that to our table. So I have my resistances filled in. Okay, the other piece of information I can see in my diagram is the battery's voltage. And that's going to be the total voltage of my circuit, 12 volts. So I can fill that in as well. Okay, the question says find the current in this circuit. I can find the current now because I know Ohm's law allows me to calculate current if I know voltage and resistance. And guess what? I have my total voltage and I have my total resistance, so I can find my total current. And in a series circuit, the total current is the same the whole time. So if I find this current for the total, it's going to be equal for the whole thing because there's only one loop. Okay, so let's go ahead and use Ohm's law. V equals I times R. V is 12 equals I times 16. Divide by 16, and we get a current of 0.75 amps. And again, that's not just the total. That's everywhere. Okay, because there's only one pathway. My current is the same everywhere. Okay, so that's the answer to this question, but now we're going to look at a follow-up question. So we just found the current, but what about this? What are the voltage drops at each of the resistors? I know they add up to 12, but I can figure out how much voltage drop happens at R1, what happens at R2, and what happens at R3. Again, I can go back to Ohm's law. V equals I times R. Now I have I and R for each of them. Okay, so at this first one, that's going to be 4 times 0.75, or 0.75 times 4, same thing, that's 3. The second one's going to be 0.75 times 10, and then 0.75 times 2. These are my voltage drops. They add up to 12, but they are 3, 7.5, and 1.5 volts. And again, when I add them up, they should add up to the battery, and they do. You can always double check it, make sure that it does, because they need to. All right, so we have now answered the next question. Those are our voltage drops. We could now find power if we wanted. We have enough information to do it, but first I'm going to show you something called a potential difference diagram. It's kind of like a graph. Okay, it's going to show the energy changes. So here is my voltage of my battery showing that I have increased my electric potential by 12 volts. And then we're going to show the drops, how much voltage is lost at V1, at V2, and at V3, and we just calculated these. So 3 volts here, 7.5 volts here, and then the last 1.5 volts here. Again, it's just a quick little representation of the energy changes throughout the circuit. Okay, and so you can see that how much voltage drop at each of them, and it should end up back at 0. Okay, that's again one of those laws we talked about, is that the sum is technically 0 because this is positive 12 and these end up being negative 12. Okay, but just a diagram you should figure out how to read. All right, so let's do the power now. Back to our table. Let's find power. Power is voltage times current. So for each of them, I have a voltage and a current. 3 times 0.75, 7.5 times 0.75, 1.5 times 0.75 gives me powers of 2.3, 5.6, and 1.1. And I can find my total power by adding these 3 numbers together or by doing my total voltage times my total current. Either way, it is 9 watts. Okay, so again, be able to do all these calculations. And guys, listen up because I have one more important thing for you to add to your notes. Okay, if each resistor is a light bulb, which is the brightest? I'll need to write this down. Brightness is determined by power. Okay, always. Brightness is determined by power. Now for a series circuit, power, remember, is voltage times current. In a series circuit, the current's the same everywhere. So in a series circuit, the brightness is going to be determined by your biggest voltage drop. But it's still whichever one has the most power. Okay, the biggest voltage drop will be where you have the most resistance. That's why when you hooked the bulbs up in class, the one with more resistance was brighter. The other one almost went out all the way, if I recall. It was really dim if you could see it at all. Okay, but in series, the one with the most resistance will be brightest because it has the most power. And again, we did those calculations here. Most resistance, most power. All right, so add that to your notes. Power determines brightness. In series, that's the most resistance. All right, guys, for the rest of the class period, which honestly, you're not going to have much time to look at this if you haven't already opened it. But you do have this assignment, 1104.1 Circuit Basics Problem Set. If you've already looked at it and you have any questions, please let me know before you leave. Otherwise, you can work on this at home, or you're welcome to come in for tutorials after school today.